It is not a star. You cannot point a backyard telescope at it. It has no surface, no edge you could stand on, no light of its own that reaches your eye. It covers roughly 125 degrees of the sky. That is more than a third of everything above you, horizon to horizon, in one continuous piece. It is not a galaxy. It is not a cluster of galaxies. It is not even a supercluster. It was here before the sun. It was here before the Earth. It was here before a single atom of the carbon in your body had been forged inside a star. Measure it end to end, and you get about 10 billion light-years. The observable universe is about 93 billion light-years across, so this one object takes up something close to a tenth of everything we can see, and that is the problem, because our best model of the universe says an object like this should not be able to exist. The upper limit, the size at which the cosmos is supposed to smooth out and stop building things, is around 1.2 billion light-years. This is roughly 8 times larger than the ceiling. The researchers who found it are not using words like interesting or unexpected. They are using words like anomalous, problematic, and it challenges the cosmological principle. That last phrase sounds polite. It is not. The cosmological principle is one of the load-bearing assumptions underneath modern cosmology. This is the story of the Hercules Corona Borealis Great Wall. And here is the part the headlines are not telling you. It is not just how big it is what it implies about the rules the universe is supposed to follow, including the rules that produce the galaxy you are standing in right now. It is what happened to it in 2020, and again in 2024, when the astronomers went back to check their own work, and the thing got bigger instead of going away. And it is what is going to happen at the end of this decade, when 2 observatories already under construction turn on and either confirm this structure or erase it from the map for good. That date is already locked into the calendar. Stay with me, because by the time this is over, you will never think about the phrase largest thing in the universe the same way again. To understand why this discovery landed the way it did, you have to go back to a period when mapping the universe was one of the most tedious jobs in science. In the 1980s, at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, 2 astronomers named Margaret Geller and John Huchra were running a redshift survey. The work was exactly as unglamorous as it sounds. Point a telescope at a galaxy, take its spectrum, measure how far its light has been stretched by the expansion of the universe. Convert that stretch into a distance. Write it down. Move to the next galaxy. Do that a few thousand times. Nobody expected the result to be dramatic. The prevailing assumption was that galaxies were scattered through space more or less at random, like sand thrown across a table. On small scales, you would see clumps. On large scales, it should average out into a fog. It did not average out. In 1989, Geller and Huchra published a map that showed galaxies were not scattered at all. They were arranged into sheets and filaments wrapped around enormous empty voids. And one of those sheets was a monster. They called it the Great Wall. It stretched roughly 500 million light-years across. That was the first time humans saw the actual architecture of the universe. Not a fog, a structure, a cosmic web of filaments and walls with vast bubbles of nothing in between. And the empty parts turned out to be just as strange as the full parts. In 1981, Robert Kirshner and his colleagues had already found one of them. A region in the direction of the constellation Boötes, roughly 330 million light-years across, containing almost nothing, not empty in the way a room is empty. Empty in the way that if the Milky Way sat at the center of it, we would not have discovered other galaxies existed until the 1960s. There would have been nothing near enough to see. So by the end of the 1980s, the picture had flipped completely. The universe was not sand on a table. It was foam. Thin sheets of galaxies stretched around enormous hollow bubbles, meeting along filaments, with dense knots where the filaments crossed. Then the surveys got bigger. In 2003, working with data from the Sloan Digital Sky Survey, J. Richard Gott III and Mario Urich identified something larger still, the Sloan Great Wall, about 1.37 billion light-years long, bigger than the first Great Wall by a factor of nearly 3. And here is where the trouble starts, because by 2003, cosmologists had a number in their heads, a ceiling. Theory said that above a scale of roughly 1.2 billion light-years, the universe should stop making structures. Above that scale, any patch of space should look statistically identical to any other patch. Astronomers gave this idea a name that sounds almost like a joke. They called it the end of greatness. The Sloan Great Wall sat right on the line, uncomfortable, but survivable. Then a different group of researchers came at the problem from a completely different direction, and they did not use galaxies at all. In 2013, 3 astrophysicists, István Horváth, John Hakila, and Zsolt Bagoli, working between Hungary and the United States, decided to map the universe using gamma-ray bursts. That decision is the entire reason this discovery exists. Here is the chain of physics, one step at a time. A massive star, many times heavier than our Sun, runs out of fuel. Fusion stops. The outward pressure holding it up disappears in an instant. The core collapses. That collapse forms a black hole. Material falling inward gets whipped into a disk, and the disk launches 2 jets of matter moving at very close to the speed of light, straight out of the star's poles. Those jets punch through the collapsing star and out into space. Where they collide with material, they emit gamma rays, enormously energetic light, the most energetic light the universe produces. The result is a gamma-ray burst. In a matter of seconds, a single gamma-ray burst can release more energy than our Sun will release across its entire 10 billion-year lifetime. Now here is the useful part. That much energy means you can see them from absurd distances. A gamma-ray burst that goes off most of the way across the observable universe is still bright enough for a small satellite in low Earth orbit to register it. So gamma-ray bursts work as beacons. Every burst marks a place where a massive star died. Massive stars form where there is gas. Gas collects where there is matter. So a map of gamma-ray bursts is, indirectly, a map of where matter is. The catch is that you need a lot of them, and you need to know how far away each one was. Distance is the hard half. You cannot measure it directly. What you measure is redshift. As light travels through an expanding universe, the space it is moving through stretches, and the light stretches with it. Wavelengths get longer. Colors shift toward the red end of the spectrum. The further the light has traveled, the more it has been stretched. So astronomers look for known chemical fingerprints in the spectrum of a burst's afterglow, features that appear at a fixed wavelength in a laboratory, and measure how far those features have slid. That slide gives you the redshift. The redshift gives you the distance and the look-back time. But the afterglow of a gamma-ray burst fades in hours, sometimes minutes. If nobody gets a spectrum in time, the burst is recorded but has no distance attached, and it is useless for mapping. That is what the SWIFT satellite gave us. NASA launched SWIFT in November 2004, later renamed the Neil Gehrels Swift Observatory. Its job is to catch a burst within seconds, swing its instruments around, and pin down the location precisely enough that ground telescopes can find the fading afterglow and measure a redshift, a distance. By 2013, SWIFT and its partner observatories had built a catalog of a few hundred bursts with measured distances, 283 of them, in the sample Horváth, Hakila, and Bagoli used. They sliced that catalog into distance shells. Then they asked a simple question. Within each shell, are the bursts spread evenly across the sky, or are they clumped? For most shells, the answer was even. Boring. Exactly what the model predicts. Then they got to the shell at redshift 1.6 to 2.1, light that has been traveling for roughly 10 billion years. In that shell, the bursts were not spread evenly. 19 of them were piled into one region of sky, in the direction of the constellations Hercules and Corona Borealis. Statistically, that region should have held around 4 or 5. 19 bursts where the model says 4. They ran the statistics. The probability of that clustering happening by pure chance came out to less than 1 part in 100. To hold 19 dying giant stars in one region at that distance, you need a concentration of matter spanning roughly 10 billion light-years. 10 billion light-years. Against a theoretical ceiling of 1.2 billion. That is the whole discovery in one line. Now I want to be precise about how hard this measurement actually is, because the difficulty is the reason this is still being argued about 13 years later. Start with the distance. You are looking at light that left its source about 10 billion years ago. The universe at that moment was less than a third of its current age. Every galaxy you would find inside this structure has spent 10 billion years doing something else since. We are not looking at what the Hercules Corona Borealis Great Wall is. We are looking at what it was. There is no follow-up visit. There is no closer look. Nothing we build will ever go there. Even at the speed of light, the trip is impossible in any sense a human can use the word. The information we have is the information that arrived, and that is all we are ever getting. Second constraint. Gamma-ray bursts are rare, and they are random. You cannot schedule one. You cannot request a burst in a region of sky you want to study. You wait, and space decides. Third constraint, and this is the serious one. Swift does not see the whole sky equally. It has an orbit, a pointing schedule, a field of view. Some patches of sky get more observing time than others, and a burst only enters the catalog with a distance attached if a ground telescope managed to catch the afterglow before it faded, which depends on weather, on time of night, on which telescopes were free. So the map has holes in it that have nothing to do with the universe and everything to do with us. And there is a fourth constraint that almost never gets mentioned. The 19 bursts in this cluster did not go off at the same moment. They are spread across a redshift range from 1.6 to 2.1, which corresponds to a span of well over 1 billion years of cosmic time. So when we say the structure is 10 billion light-years across, we are describing something assembled from snapshots taken at different moments, in different places, and then flattened onto one map. It is a little like photographing a crowd over the course of an afternoon, one person at a time, and then asking whether they were standing in a line. That is not a flaw in the method. It is the only method available at this distance. But it is the reason the size estimate carries uncertainty, measured in billions of light-years, rather than millions. This is exactly the objection that arrived in 2016. Researchers including Christopher Ukwata and Przemysław Wozniak looked at the same data and argued that the clustering could be an artifact of that uneven sky coverage, not a wall of matter, a wall of observing bias. That objection is not a small one, and it has never been fully closed out. When you hear a number like 10 billion light-years, you should also hear the asterisk next to it. So the original team did the thing you are supposed to do. They went back with more data. In 2020, Horvath and colleagues repeated the analysis with a substantially larger catalog of bursts, well over 500 with measured distances. If the original signal was noise, more data should have washed it out. It did not wash out. The clustering was still there, in the same region, at the same distance. And in 2024, further analysis suggested the structure might extend even further than the original estimate. That is the uncomfortable pattern. Every time the sample gets better, the thing that should not exist refuses to leave. Let me explain why the 1.2 billion light-year ceiling matters. Because if you do not understand that number, the discovery is just a big number with no teeth. Modern cosmology rests on an assumption called the cosmological principle. It says two things. 1, the universe looks the same in every direction. 2, on large enough scales, it has the same density everywhere. This is not a philosophical preference. It is the assumption that makes the equations solvable. Almost every number you have ever heard about the universe, its age, its expansion rate, how much dark matter it contains, comes out of models that assume the cosmological principle holds. Simulations of how structure grows under gravity, starting from the tiny density ripples we can measure in the cosmic microwave background, give a maximum. Gravity has had 13.8 billion years to work. In that time, it can pull matter together across a certain distance and no further. The number that falls out is somewhere around 1.2 billion light-years. Above that, everything should be smooth. A structure of 10 billion light-years is not slightly over the limit. It is roughly 8 times the ceiling. If you imagine the ceiling as a fence, this is not a fence hopper. This is something standing next to the fence that makes the fence look like a garden border. And researchers still cannot fully explain how gravity could have assembled it in the time available. That is not a gap someone is about to close with a clever correction. It is a genuine open problem. There are only a few ways out of it, and none of them is small. The first is that the detection is wrong, and the clustering is an artifact of how we observe. That remains a live possibility. The second is that the structure is real, and the simulations are missing something about how matter clumped in the early universe. That would mean revisiting assumptions about dark matter, or about the initial density ripples, or both. The third is that the cosmological principle itself is only approximately true, that the universe is smooth enough for the equations to work in most contexts, but not smooth in the strict way we have been assuming. Pick any of the three, and something in the textbook has to be rewritten. The only reason this is not a crisis is that nobody has been able to prove which one it is. Numbers this size stop meaning anything, so let me anchor them. Light from the sun takes 8 minutes to reach your face. The nearest star system beyond ours is a little over 4 light-years away. Our galaxy, the Milky Way, is roughly 100,000 light-years across. Now stack Milky Way's end to end. To cross this structure, you would need 100,000 of them, lined up in a row. Put it another way. Take the entire observable universe. Everything, every galaxy we can detect in any direction, 93 billion light-years from edge to edge. This one structure spans about a tenth of that. If the observable universe were a football field, the Hercules Corona Borealis Great Wall would be a stripe roughly 10 yards wide painted across it. And here is the part that breaks intuition. It is so large that light cannot cross it in a time that means anything. If something happened at one end of this structure, and the news traveled at the fastest speed the universe allows, it would take 10 billion years to reach the other end, which is longer than the Earth has existed. Roughly twice as long. The two ends of this object have never been in contact. Not once. Not in any way physics permits. Which raises the obvious question. If the two halves have never been able to influence each other, how did they end up part of the same structure? Nobody has a settled answer. Now I have to be careful with a word I have been using, because the word is doing something misleading. Structure. When you hear that word, you probably picture something held together. A bridge. A skeleton. Parts connected to other parts, acting as one thing. That is not what this is, and it is not what the Sloan Great Wall is either. The Hercules Corona Borealis Great Wall is not gravitationally bound. Its parts are not orbiting a common center. They are not holding onto each other. The expansion of the universe is pulling the whole thing apart faster than gravity can pull it together, and has been for its entire existence. What it actually is a region where the density of matter is measurably higher than the average, a thickening in the cosmic web, a place where the foam is denser than it should be, over an area far larger than the foam is supposed to organize itself across. Some cosmologists argue that this makes the whole debate less dramatic than it sounds. If it is not a bound object, they say, then calling it the largest structure in the universe is a category error. It is a pattern, not a thing. Others point out that the cosmological principle does not care whether a region is bound. The principle is a statement about density. It says that above a certain scale, density variations should average away to nothing. A 10 billion light-year density excess violates that, whether or not gravity is holding it together. So the honest summary is this. Whether the Hercules Corona Borealis Great Wall counts as an object depends on your definition. Whether it counts as a problem does not. The excess in density is the anomaly, and it is the anomaly either way. This is the kind of distinction that never survives a headline. It matters anyway. If this were the only object breaking the ceiling, you could file it under statistical fluke and move on. It is not the only one. In 2021, Alexia Lopez, then a doctoral researcher at the University of Central Lancashire, was studying quasar absorption lines, the fingerprints that intervening gas leaves in the light of distant quasars. She found an arrangement of them curving across the sky in a near-perfect arc, the giant arc, roughly 3.3 billion light-years long, nearly 3 times the ceiling. Then in 2024, she reported a second one in the same general region of sky. The Big Ring, a ring-shaped arrangement with a diameter around 1.3 billion light-years and a circumference around 4 billion. 2 structures, both above the limit, both sitting in the same neighborhood of the sky, at a similar distance. And in February 2025, a team led by Hans Böhringer described a superstructure they named Quipu after the Andean knotted cord recording system, around 1.3 billion light-years long, and by mass, one of the largest single structures ever catalogued. Add the Sloan Great Wall from 2003. Add the original Great Wall from 1989. The pattern is not one anomaly. The pattern is that every time our surveys get deeper, we find something bigger than the previous thing, and the theoretical ceiling keeps getting stepped over. Either the universe is a great deal lumpier than the model allows, or there is something systematically wrong with the way we survey it. Both possibilities are interesting. Only one of them is comfortable, and the Hercules Corona Borealis Great Wall is still the extreme case. 10 billion light-years, 19 bursts, 125 degrees of sky. Nothing else in the catalog comes close. I want to slow down on that number 19, because it is doing an enormous amount of work. We do not have a photograph of this structure, there is no image. Nobody has resolved a single galaxy inside it and confirmed it belongs. What we have is 19 points of light that arrived from roughly the same direction, from roughly the same distance, over the course of years of monitoring. Each of those 19 points is the death of a star far larger than the Sun. Each one is, in itself, one of the most violent events the universe can produce. And each one is being used here, not as an object of study, but as a pin in a map. 19 pins, where the model expected 4 or 5. From that, we infer thousands of galaxies, trillions of stars, an unknown number of planets, most of which formed, aged, and in many cases were destroyed long before the Earth's surface cooled. That is an enormous inference to hang on 19 data points. And the researchers know it. This is why the debate is still live, and why the honest description of this structure is not the largest object in the universe, but the largest candidate structure, detected by a method with known limitations, that has survived every reanalysis so far. That is a less exciting sentence. It is the accurate one. And there is something worth sitting with in those 19 points. Every one of them is a star that was already dead 10 billion years ago. Their light has been crossing empty space since before the Sun existed, since before this galaxy's disk settled into the shape it has now. It passed through the region where the Earth would eventually form, long before there was an Earth there to block it. It arrived at a satellite in low orbit, built by people, pointed at nothing in particular, waiting. 19 times, over years, that satellite recorded a signal from the same corner of the sky. That is the entire foundation for the claim that the largest known structure in the universe exists. 19 accidents of timing, caught by a machine that happened to be looking in the right direction. Here is the part that connects to you directly, and it is not a stretch. The Milky Way is not floating alone. It sits in the local group, which sits inside the Virgo supercluster, which in 2014, a team led by Brent Tully showed is itself a lobe of a much larger flow of galaxies they named Laniakea, around 520 million light-years across. Every galaxy in Laniakea is drifting toward a common gravitational focus, including ours, including the Sun, including the ground under your feet. So we are already, measurably, part of a structure vastly larger than anything we can see with the naked eye. The only question is, how far up that ladder the structures go. The cosmological principle says the ladder has a top rung around 1.2 billion light-years. The Hercules Corona Borealis Great Wall says either the ladder keeps going, or our method of counting rungs is broken. If the ceiling is wrong, then the models that gave us the age of the universe, the expansion rate, and the amount of dark matter all rest on an assumption that does not hold at the largest scales. None of those numbers become worthless, but every one of them acquires an error bar nobody has properly measured yet. That is what is at stake in a cluster of 19 gamma-ray bursts in the direction of Hercules. So how does this actually get settled? Not with gamma-ray bursts. There will never be enough of them, and the sky coverage problem does not go away by waiting. It gets settled with galaxies. Tens of millions of them, mapped with distances, across huge patches of sky, using instruments that observe on a schedule instead of waiting for a star to explode. 2 of those instruments are already working. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is surveying a third of the sky to build a 3-dimensional map of how matter is distributed across roughly 10 billion years of cosmic history. That is precisely the era where this structure sits. The Vera C. Rubin Observatory in Chile released its first images in June 2025 and is beginning a 10-year survey of the southern sky, imaging the entire visible sky every few nights. And NASA's Nancy Grace Roman Space Telescope, expected to launch by the second half of this decade, is designed to map large-scale structure with a field of view around 100 times larger than Hubble's. By the early 2030s, we will have galaxy maps deep enough and wide enough that the argument ends. Either there is a genuine concentration of matter in the direction of Hercules and Corona Borealis at that distance, or there is not. And notice what that means. This is one of the rare open questions in science with a genuine expiry date attached. Not a vague someday, a survey with a published schedule, running on instruments that already exist, that will produce the deciding data within about 10 years. If the structure survives, the size limit on cosmic structure has to move. and a lot of careful work built on top of that limit has to be re-examined. If it does not survive, then a decade of headlines about the largest thing in the universe turns out to have been a story about our own telescopes rather than the cosmos, which would also be worth knowing. Either result is a real answer. That is more than most anomalies ever get. And whichever way it goes, the structure itself does not care. It has been sitting there for 10 billion years. It will still be there when the answer arrives, still stretched across a third of your sky, still invisible to you on any night you care to look up. So what does all of this actually add up to? One region of sky, 19 bursts, 10 billion light-years, against a limit of 1.2 billion that our best model says should not be crossed. The largest structure we have ever found is not a thing we can see. It is a statistical shadow, cast by 19 dying stars, across a third of the sky above your head. It has survived a decade of people trying to make it go away, and the honest position is that we do not know whether it is real. That uncertainty is not a weakness in the science. It is the science, working exactly as it is supposed to. What we do know is this. Every single time we have built a better instrument and looked further, we have found something larger than the last thing we thought was the largest. 500 million light-years, then 1.3 billion, then 3.3 billion, then 10. We have surveyed a small fraction of the sky to this depth, which means it is genuinely worth wondering what the rest of it is hiding too. If you want more of this, subscribe and turn on notifications. Everything on this channel is grounded in real published research rather than exaggerated headlines. No hype, just what the data actually shows, including the parts we still cannot explain.